Hi everyone. Today we're going to look at lesson 3.7, angle side theorems. The focus of today's lesson is that we have a couple of new theorems for you. You're welcome in advance. That look at the relationship between angle measures and side lengths in triangles. We're going to establish what those relationships are in today's lesson. So first, let's look at a warm-up problem. True or false, justify your reasoning with a statement. So we've got two statements here that we need to evaluate. I want you to look at them, say whether they're true or false, and justify means explain. So with a sentence or two or a diagram, explain why each of these two statements is true or false. Go ahead and pause the video right now and look at that. Okay. Let's start with statement number one. Every equilateral triangle is isosceles. Okay. First, we need to define our terms, right? So an equilateral triangle, we know, has three congruent sides, right? Okay. And we know that an isosceles triangle has at least two congruent sides. Okay. So if I have an equilateral triangle, is it necessarily isosceles? Well, I like to draw a diagram too. So I'm going to draw just one example of an isosceles, of an equilateral triangle over here. Let's say that we had a triangle where every side length was 5. That's an equilateral triangle. Is that also an isosceles triangle? Yes, it has at least two congruent sides, so by definition it is. So in this example, it's a true statement. Would this be for any? No matter what measures I put in there, whether each side was 9, each side was 10, no matter what value I put in for the sides of an equilateral triangle, I'm starting to visualize that it's always going to be isosceles, right? So we can confidently say that this statement is true. How about number 2? All isosceles triangles are equilateral. Okay. Same definitions, right? Isosceles has two congruent sides, and we know that equilateral has 3. Well, let me draw a little diagram for this. What if I had an example where I had an isosceles triangle where 2 of the sides had measures of 8 and the third side has a measure of 7. That is an isosceles triangle, but is it equilateral? No, it's not. So right there, I just came up with a counterexample, which is a super powerful tool in geometry and life. So we can immediately jump to this is false. All you need is one counterexample to prove that a statement is false. And we can come up with any number of counterexamples here, but here's just one. That first one, try as I might, I cannot come up with an example that proves that one false. Anytime I have 3 congruent sides, I certainly have 2. Okay. All right. So there we go with that warm up. Now let's jump into our lesson. Right away, we've got 2 triangles with various markings. I want you to make a list of things that you notice about these triangles, okay? So at this point, I'd like you to pause the video, just make a quick list of everything that you notice about these triangles. Okay, I'm gonna start my list and say, each triangle has 2 congruent sides, right? I certainly notice these sides are congruent in this triangle, and these sides are congruent in this triangle. I'm sure that you noticed that based on the markings. I also noticed that each triangle has 2 congruent angles, right? We got these 2 angles that are 70 degrees here, and we also have our two 55-degree angles in the other triangle. Okay. So each triangle has two congruent sides and two congruent angles. Now I want to put an even finer point on this. Notice where the congruent angles are in relation to the congruent sides. In other words, looking at our first triangle, I'm noticing that the congruent angles are across from the congruent sides. And vice versa, right? I could draw it this way in the other one. The congruent sides are across the triangle from the congruent angles. I feel like that has to be important, and it is. That's the basis of our theorems in today's lesson. So from this example, we're going to jump right into our two theorems today. So here they are. First one says if two sides of a triangle are congruent, then the angles opposite the sides are congruent. Okay? So looking back at our example, both of these triangles we see have two congruent sides, and across from them, opposite from them, are the two congruent angles. It also holds that the converse of this is true. If two angles of a triangle are congruent, then the sides opposite the angles are congruent. And we also have this in symbol form here too. So if we look at this, this is basically saying the same thing as the first theorem. If two sides of a triangle are congruent, then the opposite angles are congruent. Another way to say this, and we do, is that sides imply angles. So if you have those two congruent sides, then the opposite angles are congruent. We also have the symbols work the other way. If two angles of a triangle are congruent, then the sides opposite the angles are congruent. And this we can also rephrase saying angles imply sides. Now, we can prove these theorems. It takes a little while. It involves reflexive angles. It involves reflexive sides. It involves twisting the triangles. We don't have the time in this video to do the actual full proof. You're just going to have to take my word for it today. Trust me, I'm a geometry teacher. I can prove these theorems. But for today, we're going to accept them just at face value, and we're going to work with them in proofs and in problems. So, moving forward, take a look at these two diagrams, and then we want to answer the questions. Which angles are congruent on the first diagram, and which sides are congruent on the second diagram? Go ahead and pause the video right now and answer those two questions. Okay, looking at triangle on the left side, I see my two congruent sides here, and I know based on my theorem that the opposite angles should be congruent. So that should lead me to angle B there, and that should lead me to angle C there. So angle B is congruent to angle C. We can also, of course, write that. I think it's a good habit to write out all three letters if you have them. So we can also say, for example, angle ABC is congruent to angle ACB. Both of these are correct, right? Both of these are correct. But if you want a more complete answer, use all three letters for the angle. Now moving over to the other diagram. Which sides are congruent? Well, here we were given two congruent angles, X and Y. And using our theorem, we want to again move across opposite side so we can identify segment ZY. And we can also identify segment ZX as being congruent. Okay. So that's how you use sides imply angles on the left and angles imply sides on the right. Okay, that gave us those congruent. We'll mark up our diagram. All right. Now let's go ahead and apply this in a proof. Two givens, and we're trying to prove that segment AC is the median to the base of angle ABD, of triangle ABD, sorry. Go ahead, pause the video right now, lay out the proof, see how far you can get. Okay, let's go ahead and start, of course, with our givens. So we have angle B is congruent to angle D, and that's given. We always want to be in that good habit. I know that already we're in that good habit of marking up the diagram as we move through the proof. So we mark our congruent angles there, and we also have the given of segment CA bisects angle BAD. All right. Now, you've given this already some thoughts. You've looked at it. What I always do when I come across a proof, I've got a very obvious given, right? Number one is very obvious. I already marked it. The second given looks like it's going to lead me somewhere. It's a bisection. Now, I know that bisection is going to give me a couple of, if the angle is bisected, I know that that's going to give me a couple congruent angles. So I want to lock in right away and see where those are. So if angle BAD is the one that's bisected, then I can see here that BAC and CAD are going to be my congruent angles, right? So I'm going to go ahead and write that out in the next step. So angle BAC is congruent to angle CAD. And then here we just want to use our definition of bisection, right? So we want to say if an angle is bisected, then it is split into two congruent parts. And that's what we have here. The congruent parts are angle BAC and angle CAD. Okay. Now I have two congruent angles. I can see where I want to get at the end. If I want to prove that AC is a median, I know I'm going to have to prove that this segment is congruent to this segment, right? Because that's what a median does. It bisects or divides the opposite side of a triangle into two congruent parts. But how do I go about proving that? All right, I'm seeing in my mind that if I can get these two triangles congruent, if I can get the two triangles congruent in this problem, then I think I can use CP/CTC. But how do I get there? I've got two angles. My only option when I have two angles is angle side angle. That's pushing me to the conclusion that I need to get segment BA congruent to segment AD. But how do I do it? Wait a minute, I have a shiny new theorem that I can use. Now here's where you have to look at this triangle in its entirety, right? Let's draw a big border around triangle BAD, the large triangle, because we have to use this here, right? So what we want to do is notice that in the triangle BAD, that these congruent angles lead us to congruent sides. And that's using our shiny new theorem. So we can now say that segment BA is congruent to segment AD, And that's because if two angles of a triangle are congruent, then the opposite sides are congruent. And we can use those symbols there. We don't have to write out that whole proof, every word in the proof. We can use the symbols to shorten it up for us, okay? All right, now there's a lot going on in this diagram, but now you can see that the two triangles can be proven congruent. We now have angle, side, angle, and I want to make sure, so I want to hunt down those steps that I used. So let's do this. This was an angle step. Given number one was an angle step. Step 3 was also an angle step. This step 4 was our side step. So those are our steps. So let's go ahead and say that triangle BAC is congruent to triangle DAC. And here we're using angle, side, angle. And we've already started and identified those 3 steps, which are 1, 3, and 4. Okay. So now we've proven the triangle's congruent. Now we're in great shape. We talked about that we needed to prove those 2 segments that are marked in yellow. We need to prove those congruent to get to our proof statement. So we're ready to do that right now. We can say that BC is congruent to CD, and that is because of our trusted friend, I almost made the mistake everybody makes, corresponding parts of congruent triangles are congruent. We are still writing that out for the time being. Soon we will let you shorten that, but not yet. All right, now we've got these 2 segments congruent. Now we look and we say, okay, we're now ready to talk about AC being the median to that large triangle ABD, because it's got everything that's in the definition. It's drawn from the vertex, which is A up at the top, and it splits the opposite side, which is BD, into 2 congruent sides or 2 congruent parts, all right? So that does what a median does. So we're going to go ahead and call it one. So AC is the median to the base of triangle ABD. And now we've got that pretty lengthy definition, right? We have to write out the whole thing. So if a segment is drawn from the vertex of a triangle, which it is here, vertex A, and splits the opposite side into 2 congruent parts, which it does. It splits BD into BC and CD, which are congruent. Then it is a median. Okay, and that's how we apply that new theorem. All right, let's move on. Now we want to look at this diagram of triangle ABC, and we've got 2 givens. And again, we're going to mark up our diagram immediately, right? So we're told that AC is the longest side. So I'm going to go ahead and mark that up. And we're told that BC is the shortest side. Now we know by now in geometry, right? Don't believe your eyes. It doesn't look, BC doesn't look like the shortest side, right? The way it's drawn, but that doesn't matter. We go by the givens. We don't go by what the diagram looks like. So the question we're asking right now is which angle of this triangle is the largest? And we're also going to ask which angle is the smallest. And how do we know? Okay, so we established a relationship between sides and angles with our theorem. The theorem talked about if two sides are congruent, then the angles across from them or opposite of them are congruent. So if we're dealing with an inequality situation here, what would make sense if we went across the triangle? If we looked at the angle opposite the longest side, shouldn't that be the largest angle in the triangle? And the answer is yes. So angle B we're going to identify as our largest. And the reason is that it is across from the longest side. All right, so carrying that logic forward, the angle that's the smallest, it would only make sense if that angle were across from the shortest side. So let's go across from the shortest side, and that looks like it's going to be angle A. And again, the reason, how do we know? It is across from the shortest side. All right. That may make intuitive sense to you. It may not. If you want a little example for how to physically look at this, try this right now. Put your hands together, palms together, almost like you're praying for a good grade in geometry. Okay, now I want you to open them up. Keep the heels of your hands pressed together, but let the tips of your fingers move farther and farther apart. You can see that you're making an angle between your wrists, right? Almost like a hand angle. And notice as you open and close that, open it wider and wider and see how the angle is getting bigger, right? The angle is getting larger where your wrists meet or where the heels of your hand meet. And if you drew that third side of the triangle between the tips of your fingers, that side is getting longer as the angle is getting bigger, okay? Now, if you close it back up and make a very small, narrow angle, you see the distance between your fingertips is shorter and shorter. So a smaller angle corresponds with a shorter opposite side, and a larger angle corresponds with a larger opposite side. So that's a good way. You know, hand triangles, hand angles, great way to visualize stuff. You should do that all the time. All right, let's look at one more proof. Now, this proof might look familiar to you. We've done a very similar one in the past. So go ahead, pause the video, do this proof, and then we'll look at it together. Okay, so looking at our two givens first, we have that segment MH is congruent to segment TH. And we're, of course, marking that up as we go. There's our two congruent segments. Now we're going to put the other given, angle MHA is congruent to angle THA. And being careful to find the vertex in the right place. That's this angle and this angle. So we've got two congruent sides and two congruent angles. And we're just trying to prove these two triangles congruent. So we look like we're pretty close, right? We just need one more set. We either need congruent sides or we need congruent angles. Now, because of today's lesson, my brain is geared. I'm all of a sudden seeing, okay, look, if I look at this large triangle, which we can call HMT, I'm seeing that new theorem. It's jumping out at me, right? I'm seeing that if I go across the triangle from these two congruent sides, I can create congruent angles. So I can say that angle HMA is congruent to angle HTA. And this is the converse of what we used in the last proof. This is if two sides of a triangle are congruent, then their opposite angles are congruent. All right? Okay. That's exactly what we needed. I'm going to identify the steps just to make sure. I think I'm there at the proof statement. So this was a side step. This was an angle step. And this was an angle step. All right. And the side is included between the two angles. So I know I've got a good ASA situation here. So I'm going to go ahead, jump right to the proof statement and say triangle MAH is congruent to triangle TAH. And that is because of ASA. And the steps that we start are 1, 2, and 3. Notice, guys, any proof that you're doing, in order for these steps to be used in ASA or SAS or SSS, they've got to have congruencies in them, right? Make sure that those are the steps that said that those specific sides or angles were congruent to each other and that they are part of the triangles that you're trying to prove congruent. Because in this case, we were looking to prove this triangle congruent to that triangle. Okay, and we used the big triangle to do that. We used the large triangle HMT to do our if sides then angles theorem. Now, I can already hear some of you. I think I can hear you all the way from your house. You're screaming at me, Mr. Morris, we could just use reflexive property with segment AH. Why do we have to use this other thing? If you did it that way, that's correct. We've already done this proof, and that would give you side angle side. So yes, stop shouting at me. You are correct. You could use SAS and use the reflexive property. However, we're trying to teach you something new today, a new tool, a shiny new theorem for your bag of theorems. So just know that there's more than one way to do things to prove, to finish proofs in geometry sometimes. So this is an example of a proof where there's two different paths you can take. You can go SAS or you can go ASA. We've just taught you how to do ASA today. You're welcome. All right, to wrap it up, our new theorems, sides imply angles and angles imply sides. Go ahead and use the symbols in the proofs like we did today. Just remember the most important thing, the thing you must never ever forget. Both sides and both angles need to be in the same triangle. You should probably highlight that because that's actually a common mistake that people try to use these theorems when they're looking at angles in totally different triangles or sides in totally different triangles. So make sure that the sides and the angles exist in the same triangle before you try to use these two new theorems that we showed you today.